And I say, welcome to lecture number 19. And we've been so-called quantizing the real scalar field. And I said many times I didn't like the term quantizing, so I'm starting now again with my review with just writing down some statements about operators. So this is a review from last time. It's the 6.1, the real scalar field. That's what it's called. Real scalar field. So let's say I give you some operator called H. It's of course the Hamiltonian operator. This is made up out of another operator called pi and phi. And there's an m term. All right, some constant m, whatever that is. So this thing is acting on some vector space. And I'd like to know the eigenvalues and the eigenstates. It's a little bit like, you know, I'll give you H is some, I don't know, matrix there, and ask you what are the eigenstates and the eigenvalues, and then you start. And so that's what the starting point. We have some operator that acts on some space, find the eigenvalues. However, it's not exactly this, because there you could really start. Here we need to know something about these phis and pi's. And they don't tell us much. They just tell us that that most of the time the order doesn't really matter. So there's a phi for every point in space labeled by x. And so if you apply the phi operator to the element of the vector space, to its so-called state, at different locations in different order, it doesn't really matter. And the same for the pi's. Right. But if a pi and a phi meet, let's say phi first, then you almost always get 0, except when they're at the same point. This is you couldn't hear. Hello? Was that the comment? The microphone. Who, Mr. What's your name?
Hello, Brescher. Can you hear me now?
I think it reconnected at some point.
Oh, well, thank you for paying attention. I don't know what this Zoom thing does. Oh, sorry. All right, you can hear us, right?
Yes.
I was doing infinities, so we somehow have to subtract them, but it has to make sense somehow. And the procedure just says it's around. You add these colons, which means normal order of the thing, and normal order means switch the order of the creation and annihilation operators such that first you have the creation operators and then the annihilation operators, because the annihilation operators will then on the right side act first on the state, and in the vacuum they get killed. So if I have this thing around, it just means we turn them around, and we just turn them around, not using this property, which would otherwise give us this delta of 0. And then we have 2 of them, and then the 2 goes away. So the real H, which if you didn't like that I messed with this h, you could also call h prime, right? Because then this was the definition of h in this form. That is equal to the one without the colons, without the normal ordering, and you know. So we end up with this e p vector, and then I'll use a dagger p a p. And now we have states that are just created by we can just add with any number of p's of a p's onto this zero state, onto the vacuum, the n, and then that is an eigenstate of this h with energy. E is just the sum, it's always this thing. It's the sum I from 1 to n, this 1 to this n, p vector I. There it is. And these particles, we'll call them particles because they have some energy. Soon they will have a momentum, and they have this dispersion relation, and then they really will be particles. So this is the multi-particle state because we have n quanta of energy. They are bosons because of this commutation relation. So if this is a dagger on both sides, a dagger, then they get 0 in the commutator. So here's P1 and there's P2, say, and you can reorder them. So they're automatically, these states are automatically symmetrized in the P's. Just because this is equal to the one in the opposite order. And you could write half this plus the other order. So it is symmetrized. Not explicitly, but implicitly because they commute. Right, in normalization, but this isn't written anyway, the normalization. And that also means if it's symmetrized, there's no problem having two P's being equal. P1 equals P2. You can have two particles with the same momentum, the same state. That's what the boson is like. When they were anti-symmetrized, you couldn't have that. And that comes out essentially because we started here saying that we have these commutators. I wanted to discuss also another operator, the momentum operator, just because that helps us get used to all of this. The inertial charge for spatial translation we found last week was minus interval 3x pi x gradient phi of x. There we wrote pi dot, but now we can call it the pi. So this is the thing. Oopsie. So this is there's a charge, completely classical. And the vector error here is the vector error there, so two components. And now we could ask, how would that look like in the quantum theory? And the first idea is, okay, let's just promote them, as everybody does, to operators. And now comes the hat, and then we have this. And then you have second thought, wait a minute, I know that pi and phi, they don't commute everywhere. So it isn't so clear to me that that was the right thing to do, because classically, when you had no hats, there was no problem writing the same thing as gradient phi times pi in this order without the hats, because these are just functions and everything is normal. And then you can say, oh, why don't I write it? Because people like this better, the pi to the right, whatever. And then they put the hats. And now it's not clear that this is the same. And what do? And this is just guessing, right? Because we were motivated from the classical theory to go to the find an expression for the quantum theory, and there's no guaranteed route. There's one thing that people came up with while ordering. It's the most democratic thing. So you have a half of this and a half of this. So all the orderings that you can think of, and then add them up with appropriate coefficients. So that would be while ordering. Or you do the normal ordering with the colons and integers. The interesting thing is that for this particular operator, the momentum, it doesn't matter. If it was angular momentum, it would matter. For this one, it doesn't. And I wanted just to write it down for you. I'll take the naive, just one term expression. Doing the while ordering is just very lengthy because you double everything. So if I have this guy, e to x pi x gradient phi of x. Now we have to insert the Fourier transform first. And this is minus integral d3x integral d3p 2 pi to the third d3q 2 pi to the third. Then I guess just pi of p. And it comes with this exponential e to the I p times x. And then we have the gradient of phi of q. And that comes with its own exponential iq. It's the same x because it's the same x here. And that's the derivative with respect to the x. So this gives us down in iq. I suppose I should have. I don't know if this was the cleverest. In the end, I want the oscillators. I'm not sure if I wanted to go splits. Anyway, I started. At some point, I will have to also write this in terms of the A's. It really doesn't matter. It's just going to be the same thing. So let's keep on doing it. Like this will be replaced because the derivative by iq. So then there's no derivative anymore. Then I can perform the x integration because of this and this exponential. The x integration will give me a 2 pi third delta of those coefficients p plus q. And then I can perform the q integration using this thing, which will then set q is minus p. So doing all at once, because we've done it last time, is minus integral d3p 2 pi the third pi of p. Then we have an I, the q is minus p, and then we have phi minus q, and the exponential is gone. This 2 pi to the third is there. All right. Now, Now get away with it. I have to the A of P was defined as 1 over square root of 2 p I pi p plus dp by p. Then the dagger, a dagger is 1 over square root of 2 p minus I from here, and the yes.
Shouldn't it be
Right.
minus p and that?
This is not a Q, that's right. Thank you, it wasn't a Q in this. Now I conjugate the pi. And since the field was real last time, we saw that the conjugate is the same as this with the minus sign here. So there is pi minus p plus p vector, and this is phi minus p. And now inverting this, if you want to invert this thing, like I want to find what is phi, I want to find what is phi of p and what is pi of p. I guess then you have to if you want to find it first, then you have to insert a dagger of minus p there. Then this goes away, and then you add and subtract and do all of this. But that's not going to get you this boring. So we'll just keep the computation if I can find the answer real quick. This is 1 over square root of 2 d. I should have known this by heart. But anyway, it's a of p plus a of minus p. And this is minus I square root of p half, and then the difference, a of p minus a dagger minus p. Right, okay, so there's just 2 steps that we skipped. And now insert this on previous expression. Integral p to pi the third. This is well minus I. So it goes here. The p vector can't come out of the integral, but then and then we have the pi. More i's. Minus I square root p vector. Careful. Half 1 over square root 2 p q vector, because there's the q in there, and there's also a minus q. Here it doesn't matter. And then we have pi came first, so a dagger p minus a dagger minus p minus p, and then a dagger minus q plus a dagger p. There we go. Four terms, I guess. Equals minus nothing. The 2 and the 2 is 1/2. So with 1/2 integral d t to the pi third. This is a square root p over q, the p vector, and then a with p, a with minus. Why would we miss? There's a q again. There's the q again. All right, you wanted to complain, but didn't. Do we have audio yet? Still, so this is a p. This is a p. What would it be the q? So they cancel. How nice. Oh, nice. So they're all gone. And they have a little room to move to the left. P vector A P with A of minus P. Now it makes sense. Now I can say something. And these two together say the dagger, A dagger minus P, A dagger P. And then first and last plus A P, A dagger P, and then the inner minus A dagger minus P, A minus P. There. And now we use symmetry. I can commute the first the operators in the first line. So the AA commutes into A dagger, they commute. So this thing is it's symmetric in P goes to minus P. If I send in this term here, P to minus, change the variable, then this will be a minus, and this will become a plus. I can bring it in the other order. So it's symmetric under P goes to minus P. This factor is antisymmetric because it's just naked P. P goes to minus P is obviously antisymmetric. So this whole thing, the whole integration, is the integrand is an antisymmetric function of P. But I'm integrating over a symmetric interval or domain, three-dimensional. So this is zero. This will integrate to zero. That's just zero. And the same here for the same reason. Good, gone. And now we have kind of these numbers. So first of all, here I also want to switch P to minus P to get rid of all of these minus signs, because then it changed. I have no negatives in this argument. And even this goes away because there is this P here. Everything, this gets also a P. So I can, by changing integration constant from P to minus P, get rid of all of these signs. So then I have a plus here, plus here, plus here. Changing the given variable. And now this very much looks like the Hamiltonian we had, except that here is the P rather than the E. There was even this 1/2 under the energy. In fact, it was Lorentz invariant. It should have been just the 3 components. You could have guessed this. The difference is we don't have to come up with any stories to change this order, because we can just use the commutation relations if we wanted to. So it is this with the extra term 2 pi to the 3 delta of 0 essentially, because they're at the same point. But this is a constant. This doesn't depend on P anymore. So this is multiplied by d3p P vector. So even this number goes away, half, I guess. Who cares? This you can set to 0. It ends up infinity times 0, right? Because this is infinite. Maybe you would have stopped working here because you said, oh, wait a minute, here, infinity, I don't know what this is. You could have regularized it and said, okay, I'm not going to integrate, I'm not, I don't know, do something. And then you have a variable, a name, whatever, lambda, for this infinity, and you don't send it to infinity, and you could keep computing, and you have lambda times this, and then this is 0. Or you say, okay, I'm going to just tell you the story as we in Hamiltonian, I normal order it or do something. Whichever way, we'll get rid of this because we don't want the momentum to be measured, like for the vacuum to be measured like infinity plus something. So this is going to go, this is going to go together with them, half cancels, and then our P vector is integral d3 P 2 pi or P vector, and then the counting guys. So in the Hamiltonian, unfortunately, yes.
just to be like the terms you crossed out there, are these are symmetric, right? Or are these, did I see that they're somehow antisymmetric?
They antisymmetric because of the
Oh,
sector
I
P.
see, I see, I see.
They are symmetric. Right, the P cancels. The P kills it exactly like it does here, because we have the same momentum on the side with minus momentum there. Yes.
One question about this. So the delta distribution evaluated with P, the integral, isn't that like exactly 0 because we're evaluating this function P at 0.0, or am I wrong?
Yes, you're wrong. Because you want this.
I see it.
The integral of dx of delta of x is 1, right? You have another function of x, and then you evaluate this where that has a root. So it's f of 0. But if this is a delta of 0, then there's nothing you can do.
Also, one other question. I'm not sure if the recording's still running because we reconnected. Okay, it seems
Is it?
to run. Yeah, it's
Right. But thank you for paying attention here. I would be sad in the end if there's just half a lecture missing. I like it to be complete. Yes?
So for now, we always say like infinity to the power of 6, which is
Even if it's to the power of 24 or just a negative. All these infinities we don't want.
relation between infinities. Like if we also can drop infinities with power to 24, then
Yeah, this is to do with the space-time dimension. It was half joking. It will never be to the 24. It is all kind of related, and it is because of the continuity of things. If the p's had, like, if they were countable, even if they were infinitely many, but if they were countable, we wouldn't have a delta of 0. We would have a delta chronica of p. And then the Q is now the same, so it's P and P. And if they're the same, then it's just a 1 and not an infinity straight into your cases, right? It has to do with this continuum limit. And we just have to be careful that these limits are taken care of. Yeah. People then say, okay, let's quantize in a box. Say our universe isn't infinitely large, where you have a continuum of momentum, but we are in a box. Let this box be really, really big from here to here, and then you start to draw modes. This is the ground state, and then you go like this, and then you can write all these. Then they very small difference between them. You see, because it's such a big universe, but you still can count it, and then everything's cool. So far, yeah. Then you still have to maybe see that you don't have this ultraviolet catastrophe that Planck had, like, because the number goes up. At least you have the spacing in there, and it's a quantization in the box. You can do different things. You can also, we'll discuss this. There are factors that we can stick in, like the normalization of the phi. At some point, we'll say we have this phi. Why not put a z in front? Z is a number that we can do and send to 0 to infinity, whatever it's convenient. That's the so-called wave function renormalization. If you compute this, the whole things, what we get, the whole observables, and we have z's in the end and infinities, then we can tune the z so that we get what we want. How is that fair, right? How can we just always do what we want? Well, these are the renormalization conditions. We get a finite number of choices. We want this, and that fixes all these parameters we can stick in. And even the m, we're saying that the m in the Hamiltonian is just a number which we think is a mass because it's called m, but it is just a number. And then we do a computation, and in the end, we have like that the particle has this mass. So the mass is like this p squared here, the square of this, the formula. There'll be some way of finding out what is the mass now of our excitations. And then we see, oh, wait a minute, that's infinity. These annoying infinities, the Schauberger bear. But it is maybe infinity plus this m. Then we say this m is also infinity plus the mass that we wanted to have. And we'll see this in detail. And then the infinity and this infinity cancels, and then it leaves in the difference just what we wanted. But that fixes then this thing. And every other thing that we compute will then be in relation to our choice here. So it'll become predictive after we have fixed what we could fix as we desire. Yeah, this is probably the best way to handle these infinities. Just let them appear and sweep them under the parameter rug, and then compute with these expressions, rather than now trying to box and, well, we'll come back to the box because we kind of have to make sense how infinite is this in relation to how the infinity appears. They're called the regularization. We have to have some control, and there could be a box too. Yeah, but for now, let's just simply throw them away when they're so innocent as this, which is just offset of our scale. Like the vacuum now has zero momentum. And see, the vacuum really wanted to have zero momentum because it couldn't decide should I go left or right. If the vacuum had some non-zero momentum, it would be a component of a vector, and it would have to decide where do I go. The energy wasn't so, it didn't have this problem. It had an E here. The E is always positive, and so we couldn't have this trick that it cancels, but it didn't matter. It just said, okay, well, I'm just the vacuum. I want to be some number, and there would be no like symmetry breaking. It doesn't have to single out the direction. So that's how it happened. Now we have, okay, so our excitations that I've just erased, these things here, the A, E1, A, the N on 0. These are now things that have eigenvalues E, P, I for the energy, and they have eigenvalue P vector I, look at this, for the momentum, and the EP is this thing. So it is the dispersion relation that we have, and so they look like particles, and what looks like particles we just call particles. That's essentially it for the free theory. We'll still spend today and tomorrow working with this, trying to compute a little bit of things and getting familiar with these formulas before we go on to other theories. And well, this is kind of cut, and well, we just ask questions. You keep asking a question when they come up, right? I'll give you one. Like the first thing I want is the normalization. The normalization of these states, and let's say the normalization of single particle states. The first, so these are just this guys, A dagger of P. And start with calling this P head with a 1. What does it mean for P with Q? Q is, of course, the same thing. This is 0, then the dagger is P on the left, and then we have an A, Q, 0. And this is, how do you evaluate these things? Do you know yet how to evaluate this thing? How can we proceed there?
And I swap them with the
We swap them because we know how to swap them. And why would that help anything? A dagger Q, A P, and then since I swapped them, I have to add the delta 2 pi cubed delta P minus Q in there. So what did that help? Introduce a second term.
The second term, we can pull all the stuff out, and the first term vanishes because we have.
This is this. So this is 0, and this is a constant, and they are. This is what we have to agree on first. We say the vacuum is normalized. If it wasn't, then we would get this factor here, but otherwise we'll just have the delta function. So this 2 pi to the 3 delta 3 P minus Q. So they look, no, not they look, they are orthogonal because it's delta. If they weren't, it's not the same as 0, so they're orthogonal. And they're kind of normalized up to this constant. We could get rid of it by dividing, but that's just an innocent constant. What is more troublesome is that this is a 3-dimensional delta function. That's good for our observer in that particular frame, but this isn't Lorentz invariant this way. So what do I mean? The question I want to raise is if we have another observer, like he could observe the same particle, the same one particle states from his perspective, that they have different momenta, and they could have the momenta P prime and Q prime. So this is really just the spatial part of, how do I write this? Of the Lorentz transformation. How does this work? How does this transform? How do P transform under Lorentz transformations? Let's just do this. Let's write it in a second. Just writing the claim. P is the Lorentz transformation of. Okay, so the dumbest thing would be because I need all 4 ABCs, right? And I'm taking the P, this is the 4 vector, and then I transform it, and then I take the spatial part in there. So it's the Lorentz transform of this. So what I mean is Lorentz transform of P, and I'm going to write this in explicit formulas what this is. And the Q is the same. The Q is the momentum that the other observer measures, the Lorentz transformation of the Q. Now, what is P prime Q prime? Is this or not 2 pi to the third delta P prime minus U prime? That would be nice. I mean, we would call this then like a Lorentz invariant or at least covariant. It would just be the same form of the formula. Is this true or not? And the reason why I'm talking about this is going to be not true. Now, see, now I have your interest. This is just why. And let's make this more explicit. How does the momentum transform under Lorentz transformations? And instead of writing this in the most general, most complicated way, let's just say we have one observer, that's us, we're sitting here. And then we have another observer who's moving with respect to us in, so this is our time. I guess modern times are x0. And then this is our coordinate x vector. Someone else is moving in this direction with, I guess then it has to be, it's moving, that is the x prime 0. And then that's the x prime axis. And now I'm not sure if I'm consistent with my notes. Does it go to the left or to the right? But that shouldn't matter. It can only be opposite to what I wrote in the notes. Let's say we have this. Then the x0 prime is gamma. What? It wants to be this. Plus or minus Vx1. And I think I rather want to have the prime on this side. I'm writing the inverse. So this is a prime and this is a 1. First component of the prime one, and now you figure out if it's plus or minus. It doesn't really matter because the v could be 0, right? Could be negative. But what is it if picture is true? Then on this axis, x0 is 0. So say this is 0. Then I want to describe this line in this coordinate system is it with the plus or with the minus sign? I guess it is with the plus. Because then, if this is 0, it means that the x prime 0 has to be negative of x. So this thing, and that's true, right? If I have some positive number here, a positive number here, blah, blah, negative. Wait, I'm on this axis, and they have positive values in there. Yeah, I guess it's this. It is this. And then, so this was just to figure out, I'm not setting it to 0, this is just to figure out my sign, which is completely unnecessary. And then the 1 is gamma v x prime 0 plus x1, x prime 1, x prime 1, x2 does nothing, x3 does nothing either. Now this is how my coordinates transform. How do my momenta transform?
In the same way?
The same way. Why?
Because there are 4 vectors?
Exactly. So if they have the indices in the same place, they should transform exactly the same way. We want, yeah, scalar being there. So what do I have? I have now my P0, that's the P, so I have a P vector, I have a P mu that has P as the energy and P vector as the 3 components. This is an on-shell, what we call an on-shell momentum, because this P squares to M squared. It's not just a random thing. Here I could, so if I was in momentum space, P0, vector, I could pick anything, but if I set this thing to be the formula, the energy, then I'm somewhere on this mass shell. It could be here. I won't be there, I guess. Yeah, I won't be there. So I'm on this mass shell. So somewhere there. It's a special momentum. It's an on-shell momentum. And now, still, the energy is this. So it's E P vector is equal to gamma, and then this is the E P vector. Where's the prime go? Same thing, prime there maybe. Plus V. And then now this is the P prime component 1. Then we have the P 1, it's gamma V E P vector prime plus P prime 1, and the P2 is just the P prime 2, and the P3 is the P prime 3. And same for Q, which is an EQ vector. All right, so this is how these things transform. And I want to know what happens to this delta function that we found in the normalization of the one-particle states. This there. So I want to rewrite delta 3 P vector prime minus Q vector. Well, this was just a guess. What we had gone was below this layer of chalk. And that thing I can now write, I can insert these things here. So this is equal to delta 1. The first component of this, these are 3 deltas. The first component of this is this thing. It's gamma, and then I have V P vector prime plus, so this would be plus E, and then there will be the same from the Q, so let's subtract the Q first, minus PQ prime plus P prime 1 minus Q prime 1, that's from the Q. The gamma is everywhere, and that's the first delta function. This is just too much. And that's why people don't like quantitative. This is a or Lorentz matrix. Now the P2 is just P prime 2. The Q2 is just the Q prime 2. That's nice. And then the P prime 3 is Q prime 3. So this thing has a chance of combining to define delta 3 Q vector prime minus Q vector prime, because then this is kind of Lorentz invariant, and so this has a chance. But now we have a mess in the first delta function, and we should consider this thing as a function of P prime 1, because I want P prime vector to be here and then minus whenever this is 0. So this, all of this, think of it as a function of P prime 1. And let's find out when this is 0. Why? Because there's a formula. If you have delta of n of x, and this is, you find out what are all your roots of this f, and then for every root, you have a delta x minus xi, and then the normalization, how fast your function goes through that root. So it's the f prime through that root. And then if it goes the other way around, you just take the minus sign away. And that's it. So these are the roots. xi, all roots of f. And it is simple roots. They're not simple in your school anyway. And where are the roots? What's the value of P prime? P prime 1. The P1 is in there, hidden a lot. This thing is, so the EP is square root P prime 1 squared plus P prime 2 squared plus P prime 3 squared plus n squared. So it's there, and then there's the Q, and then there's the P prime there. It's everywhere. But since the P's and the Q's are, or the directions 2 and 3 are the same, this is the Q prime, and this is the Q1 squared plus Q2 squared plus component 3 squared plus n squared. And these delta functions set these things equal, so this is all equal. There's just this thing. If you set this to 0, it really follows that the P1 prime should be the Q1 prime. And that makes a lot of sense. If you have your 3-dimensional space, and this asks you what's the the P and the Q have to be the same vector. Now you do a Lorentz transformation, and then they move, of course. Here in this picture, they move. Well, everybody moves on their mass shell, same mass, so they move in the same thing. They move a lot. And here as well, but they will be the same at the end, right? You start from the same, so they. So what is the solution here? This setting it to 0 says P prime 1 is P prime 1, sorry, that is Q prime 1. So the root of this is really P prime 1. So that's already good. However, there's this 1 over F prime. So what we are finding here is indeed this. All 3 components of the P prime will be set to the corresponding components of the Q prime, but with 1 over F prime of P prime 1. Yeah, and primes look like 1s. So let's find this out.
We're right now taking the function as like q as the argument, right?
Now P is the argument.
But then xi is, if we have x minus x.
Yeah, then I insert, well, it's the same, right? But then I insert, I mean, that doesn't matter because the delta function sets them equal. You could put this or this. Yes. Well, I just want to be right once, so I can change it. In fact, it will look nicest if you write this vector in terms of both. You write a little. Let's see. So f of, do I need to write this now? F of p prime 1 is really this gamma v. Now comes the square root p. You know what this is. It's the square root, so it's e p prime. We're not going to forget about it to differentiate it. E p q prime plus p prime 1 minus p prime 1. And now the prime, I guess, is d by d p prime 1. And so it hits there and it hits there. I have a gamma, I have a v. And this energy, differentiating with respect to this thing, is the 1 over 2 square root. But the square root is this p. So it's 2 p prime what we had. And then the inner derivative is a 2 p prime 1. And even the 2, like it always does if you have the square root. And nothing else. And this is 0 because there's no p in there, and this is 1. And then the gamma is also once the 1. So that's what it is. And now I can pull out the e p prime. And why not? Yeah, just pull it out like the gamma, and then we have e p prime 1 plus e p prime because I pulled it out. And this is hopefully something we know. Where is it here? V p prime 1 plus e p prime and the gamma is e p. So this and this is EP. So this is EP divided by EP prime. Aha. So we know now that the delta function we found, P vector minus Q vector, for us as observers, translates into, so this is 1 over the F, and absolute value is fine because it's all positive, so it's E P vector prime over E P vector, and then delta, all the three of them, which we can combine to P vector prime minus Q vector prime. There it is. And so this shows two things. First, it really isn't invariant because the factor changes. But also it tells us what is invariant. If you multiply the thing by EP, this up here, then left and right hand side looks the same. So let's do it. We redefine our states, we rescale them. So let P, there's no error on it. P square root 2EP, the 2 is unnecessary, but I'll comment. But you want it bigger because we know we get. Well, let me write this first so that we have it at our reference. So P vector delta P minus Q is equal to EP P prime delta P prime minus Q prime. And now a factor of 2, for a reason I will just tell you in a minute. So now we have this identity, and I knew that these P's in the normalization give us a factor of pi's, but this delta. So I want to produce the delta and this. So I'll just add square root of this in there. So that is square root of 2p and then a vector p0. What is most hilarious is that this is the same as we had last time, calling it alpha. So we first had these alphas because it was easy to define them. Then we weren't happy because they were not the normal number operators. So then we divided them by square root of 2 EP to get these A's. Then we were happy that they are real number operators. But then we were unhappy because they are not producing Lorentz invariant normalized state, so we add it back in. So there's a back and forth. If you want like Lorentz invariance manifest, then I guess you want these. It's just moving things around. And for my notation, I wondered quite a bit how to do this. I don't want to have another decoration. So this is the 4 vector. And this is the 3 vector. So if this has an arrow on top, or in this notes boldface, then I mean the one with the A's, or then I mean the one with the A's. And if we add this extra factor here, which has the 0th component in there, then I decide, okay, maybe it's cool to not have the arrow, then it's all the 4 components, although you could compute it also from the vector because it's one shell. But that is kind of my convention I came up with. No errors in this before. And now this P Q is giving you 2 pi cubed, and then this squared 2 BP delta 3 C vector minus Q vector. And that's what we like. That works. Prime. Who wrote prime? And that's what we like. Because for the prime person, he would write the very same equation. Otherwise, the other person would have to write this. Yeah.
So this result now holds for general Lorentz transformations, or does it not? Because we only showed this for shift like an X direction.
Exactly. Since luckily the X direction in this universe isn't labeled as such, it could be anywhere. Or the other way around, if I have 2 reference frames that move relative to each other, you know, the axis could, I mean, whatever they do, I can choose to call the relative x, the line along which they move, the X direction, and the X prime from his or her point of view, and then it works. So it is general enough. Without loss of generality, we choose the direction of motion to be the x-axis, and then this goes through. But you could also write the general transformation, which is very complicated. I guess when you're, well, you can derive this without also different ways. You could, for example, do something like this. You write it all 4-dimensional. You know, maybe it's an integral. So you have the d4 p delta p. Forget about the q maybe. 4-dimensional, and this you write as the 1-dimensional, and then the 3-dimensional. And so you transform this, and then that, and you know, you want the same thing in the primed ones, and you want it you figure out what this is. I mean, there's several ways. I was going to say this because then you treat everything at once and you know the determinant of Lorentz transformation is 1, so when you get faster, you get the same result. You know, if you want to do it general, then it's really many entries here. You know how these things look like, ugly. But if you, and it's not necessary to do it, but if you want to do it anyway, then you should probably find a cleverer way of writing it. So in here, since in the four-dimensional case, 0 and 3, the whole transformation should be invariant because it's four-dimensional. It's already manifestly Lorentz invariant. And only if you break it up into the 0 part and the spatial part, they transform each in a non-trivial way, but their effect in total cancels. So maybe then you want to look at how does the delta 0, I mean the one-dimensional of the 0 component, how does this transform? Because then you know this is the opposite of this. I don't know. Wrong answer. The question is, it is the general proof already because I don't know where x1 is, and I invite you to do the general computation, and I also warn you that you should probably think of a better way going about than this. Yes.
Yeah, I can ask a question about annotation. Is there a specific reason why you write the dimension over the Dirac delta function?
No, because you would be able to tell from the argument that it is a multidimensional one, right?
Yeah.
You wouldn't maybe know if I'm working in 2, 3, 26 dimensions, but we always do 3 dimensions, so it should be kind of obvious. That's why I also often I really want to forget about it because it's taking time to write it and it needs space, but it's just making it more specific. It's not necessary. Is there a place where it's necessary? Well, if I write delta p, what's that? It's probably then a 4-dimensional, or is this? And then what is this? The 4 square was the second component. Yeah, I don't know. It's just sometimes I wanted to make it more clear. But as you say, it's not necessary, absolutely not in this case, because you know it's 2 vectors and it's a 3-dimensional one. Yeah. Now, I guess that's done. However, now we have the normalization screwed up with this, but this wasn't so bad before, being 1. This re-normalizing will show up other places. So you know, the other relation that goes hand in hand with this thing is the completeness relation, right? So you have P with T should be what? Just normal quantum mechanics, yell it out. Nothing, right? But what is it if you integrate? Like the sum of all of these. What does completeness mean to you? You have a complete set of states, and then it should be 1. So this you want to be 1. The unit operation change it because you want to stick it in everywhere. You want to insert it and then split it up. Say. So you have some expression and there's a state, and then you want to stick in. You want to change bases, and then you move this in there, and this gives you some wave function, and then you have to change the basis. But now, to get the 1 here, and since they are normalized strangely, you have to actually stick this in here. And then that's that as well. So all of this goes here, and now it's 1. Within the sector of single particles, single sector. Then this is the field. So if you know our state consists only of some linear combination of single particles, say, nothing multi-particle, then we can insert this thing without changing anything. But with this extra factor. And so this will be around everywhere, this thing. This combination you should remember because it is the Lorentz invariant integration over this mass shell. I'm going to draw this again. Lorentz invariant integration. So this is not next topic. This was the normalization of the states, and now this is Lorentz invariant integration. And the claim is that with this extra 1 over e, 1 over 2 e, the 2 doesn't matter, 1 over e, this is invariant. So if someone else in a boosted frame or rotating frame should write the same thing, with just primes everywhere. And I want to not massage this into something, but take another expression and then see that they'll turn out to be the same. So I start, so here, this is what I'm going to do. It's a p vector, and this is p0, and then I have my mass shell here. So this is where p0 squared is p vector squared plus m squared. Or better yet, where p0 is p vector. Why better? Because this has also negative solutions. That would be down here. All right, these two together. This and this is this and this. Doesn't make any sense because it's square root of forget it. That's the upper mass shell, and p0 equals minus p is the lower mass shell, and both together are mass shell p squared equals m squared. And now I want to integrate over this space, and I can do this by b4p 2 pi by convention, and then I'm sticking in a 4-dimensional delta function of this that sets our p's onto that red surface. So it's delta p squared minus m squared, and a 2 pi. How many dimensional is this delta function? I didn't write it. Have you figured out?
Yeah, okay, but one.
One condition, exactly. Because this is one condition. This is one scalar thing. And that is Lorentz invariant, because if you do a Lorentz transformation, then this will change by the determinant of the Lorentz transformation. The determinant is 1, be it orthogonal or proper or not proper, it's just going to be, well, we have the absolute value of the determinant. So this anything is okay. And the p squared is also Lorentz invariant, and the rest has nothing to do with transformation. So it is invariant. And now this thing I'll show is kind of that. And it will boil to the same formula with the delta functions as we had. So this thing here in there is p0 squared minus p minus m squared, and we call this now a function of p0. And now we want to find, I can essentially, see, if here was an f of p, anything, I can perform the p0 integration using this delta function. Because it's there, so I use it. And what would that be? So this is 2 roots. Setting this equals 3, or p0 equals minus p. And therefore, the delta p squared minus m squared is equal to a delta p0 minus EP, and also the delta p0 plus EP. These are the 2 roots. And now we have to divide by f prime. F prime is just 2p0. So it's 2p0 and absolute value. And then also here it's 2p0, of course. And now the top one, that's p0 to EP. That one to minus EP, but the square doesn't make a difference. So I end up with delta P0 minus P over 2 P plus delta P0 plus EP to EP. So we have two contributions, and guess what? That is the contribution of mass. So, and that then, when you're done with this integration, then we do this one with this. So I simply invite this one. Nice formula. Integral d4 p 2 pi for 2 pi delta e squared minus m squared. Some f d that is equal to the zeroth integral I will perform using this, and then I have the 3 dimensions left. I have this factor 2 pp. Now you know why the 2 is everywhere coming with the e, because it appeared here. It appeared here because it was in the derivative. And since it's here, well, they are married and then they go everywhere together. And then f of p with setting p0 equals p plus integral d3 2 pi cubed 1 over 2 p p f of p with p0 equals minus p. I don't know why there's a line there. So the integration over the mass show, which is described by this combination of symbol of a function of p, can be written as these two parts, one on the upper and lower part, and this is the factor that comes in from the conversion of the delta function. And now you see, this is Lorentz invariant. That's exactly this thing here. If you don't want both combinations, we can also single it out. We can also write like this. So delta p squared minus m squared times the theta function of p0. Theta function means if the argument is positive, then it's 1. Otherwise, it's 0. So this sets p0 to be a positive number. And now multiplying this with this thing here, it kills the second term because this wants the p0 to be negative e. E is always positive, so this wants p0 to be negative, conflicting this thing, so it's 0. And we are left with that only. So it's 1 over 2 p delta p0 minus p. So we can also just have the first term. The first term is equivalent to this thing. Now, is this Lorentz invariant? So I can add in now, yeah, is this Lorentz invariant? That was because it's the p squared, and that's a scalar. This one, I don't know. I have to ask. No, but it's nice that you're. Is theta of p0 an invariant function? So this is p0, and this is theta of p0, and it looks like this. Nothing jumps up. We don't know what it does here. Some people say it is included here, some say it's a half, whatever. Something like this is obviously different. Is that Lorentz invariant? If you change to a different reference frame, why not?
Because just like from the feeling, we don't always have the time transforms by itself. Like you get shifted and you get scaled and whatever. So
Yeah.
like if I want to know the time in the other system, then I can't just use the time that
It doesn't look Lorentz invariant. No, you're right. But is it still? I mean, it doesn't ask much, right? You can scale this, right? If I multiply this by 2, it just looks the same. It is 2, it's just stretching it, right? So I can do a little bit to it. I can do a little bit to this p. shifting is probably not good. So this is the sign, it asks for the sign of the zeros component of the four vectors. So it asks for the sign of time. Is the sign of time Lorentz invariant? Sometimes it is invariant under those funny orthochronous Lorentz transformations, but not under the others. So this thing is Lorentz invariant under the orthochronous Lorentz transformations. And that makes sense because the non-orthochronous ones will flip between two things. But if you use reciprocal to the first, one of them, then you shouldn't change the sign of it. So yes, if you just have the orthochronous Lorentz transformations, this combination is invariant, and then that by itself is good too. Time's flying. Speaking of time evolution, I can't believe it. I have 2 minutes, and that's not enough. All right. Frage. Am I going to? Yes.
Maybe then we should spend the time differently.
Yeah, perfect.
Why did we use the beta function now? Or
Oh, because now see if I have this formula, just this integrating this thing. So integrate some function over the entire mass shell. This is like both hyperbola branches. That's the integration that we do. This function, not everywhere in space, just these red lines. And that can be written as this sum, first and the second. And that also makes sense because you see in the picture that we have two branches. That's the one and the other. Now I have an expression here which looks like one of the two terms and not the other. Because the P0 in here is the EP and not the minus TP. So this, what I have here, looks like just one of the two, integration over the top branch. But in this story here, I showed that the sum is Lorentz invariant because we started here, we got both terms. But now I say, no, even the individual bits, this and this, is in a restricted sense Lorentz invariant, namely under those that don't change the sign of the zeroth component of my four vector. And these were called the orthochronous. Even though this is not time, it is still the time component, the zeroth component of a four vector. And this is multiplied by the same lambda as we had. So if this is orthochronous, if lambda 0, 0 is positive, right? Even larger than, it has to be larger than equal to 1. We show it at some point. Yeah.
But why don't the other lambdas matter? Like, it's just like if I take my P0 and I insert, I don't know, like gamma P0 prime plus VP1, then prime, then like it doesn't just depend on P0 prime. It's just.
Yeah, well, there are also the others. However, because there's more conditions, right? You know, this has to satisfy lambda, beta, lambda equals eta, and we could derive things. It's probably easiest to look at a picture. If, you know, instead of these formulas, we have now the Minkowski space, and let's be in space, I don't know, if you want P0 or T0, choose your preference x1 or p1, then we are somewhere in this space. Now, how does this move? If the rotations just rotate around the origin. The other one, do funny stuff with hyperbolas. If you have a kind of a null like vector, it just moves along here. If you're time-like, then it moves along hyperbolas there. And if you're space-like, it goes here and there and there. So these are basically your thing. So if you're sitting somewhere here and then you do a Lorentz transformation and with some rotation angle, the boost parameter, then it moves along this line. And it stays space-like, by the way. And here you can change the sign of x0. So x0 is this. By doing a Lorentz transformation, it brings you here. So suddenly it's negative. But when you are up there, then you can only drive on this hyperbola, not down. You can't switch to another branch. You go here. So if you once you're positive, you stay positive, even though there's a sum involved, and you have to have that this guy is time-like. And if it's p squared, it's m squared, that's larger than 0, that is time-like. So the time-like vectors under orthogonal don't change their sign, even though in this thing we have the 1, 0, 0, p0, and then plus other crap that could be negative, but it's never negative enough to make this negative. Yes. If you are already up here, if you were there, it would be enough to pull you down. Oh, I think these were 2 well-spent minutes then. Thank you for those questions. And we'll continue tomorrow if you want to.